Good morning, everyone. So today we will continue our discussion about special relativity. So in the previous lectures, we reviewed the kinematics of special relativity. So from today, we will start to discuss about the dynamics. But before we discuss about the dynamics of special relativity, we need to introduce, or more precisely, we need to review one important concept that is very useful for the discussion about special relativity. That is the four-dimensional space-time description. Okay. So before we go to, so basically in this chapter, we were focusing on the question, why do we need to utilize a four-dimensional description to describe special relativity? Why Newton's mechanics three-dimensional space is enough, but why do we need to go to 4D in special relativity? That's the focus of this chapter. Okay. And after that, we will utilize this knowledge and this technique to look at the dynamics of special relativity. Okay. So, but before we go to 4D, let's first do a quick revisit about three-dimensional space. Okay, so in order to learn 4D, it's a useful and a good, helpful knowledge to review something we know about three dimensions. Okay. So in three dimension, we know that in three-dimensional space, we can define the so-called 3D vectors. For example, electric field, magnetic field, force, velocity, acceleration. So many physics quantities are 3D vectors. But what is a 3D vector? Well, first of all, 3D vector need to have three components. We have three numbers written together, organized together. Okay, but this is not the full definition of a vector. Okay, so in order to define a 3D vector, having three numbers is not sufficient. For example, we can randomly chosen three numbers together. For example, we can write down a person's age, height, and weight together, and use a parenthesis to enclose these three numbers together. But that would not be called a vector. Okay. And how do we know whether a three number written together is a vector or not? It turns out the precise definition of vector requires knowledge about spatial rotation. Okay. So in 3D space, we know that we can write down the 3D coordinate x, y, z together. Okay. And once we write down this x, y, z coordinate together, we can mark any point in the 3D space. However, we also know that we can rotate our system. We can either rotate the space or we can rotate the coordinate x, y, z axis we chose. Okay, so these two types of rotation are equivalent to each other. And under a spatial rotation, or if we rotate, choose different direction orientation for my x, y, z axis, I will get another set of coordinates. Okay? So this new set of coordinates, I will call it x prime, y prime, and z prime. This original coordinate x, y, z and this new coordinate x, y prime, z prime are related by a so-called rotational matrix. If we rotate along the z-axis by angle phi, the rotational matrix will look like this. If I'm multiplying x, y, z with this matrix, I get my new coordinate x prime, y prime, z prime. Okay. So this is the so-called rotation along z-axis, RZ rotational matrix. If we rotate along x-axis, we use this rotational matrix. If we rotate along y-axis, we use this rotational matrix. Nevertheless, we use some 3x3 matrices to represent the rotation. And this rotational matrix tells us how this coordinates transform under spatial rotation. Okay. And of course, we can also define the inverse transformation. The inverse transformation, we just utilize the matrix inverse. The inverse matrix transfer us back from the x prime, y prime, z prime coordinate back to x, y, z. Okay, so r goes from x to x prime, and r inverse goes from the prime to the original. Okay, so this rotational matrix turns out to be the key in the definition of vectors. Okay. So for other physics quantities, as long as it satisfies two conditions, we will call it a vector. First of all, we can organize three numbers together. We need three numbers to define a vector. That's always the case. And the second and the more important condition is that under spatial rotation, if we rotate our space, or if we rotate the orientation of my XYZ axis, these three numbers need to transfer exactly the same as my coordinate XYZ. Okay? So we know under spatial rotation, XYZ becomes x prime, y prime, z prime, and their relation is this rotational matrix R. Okay. So for this physics quantity, these three components also need to transfer under spatial rotation and using exactly the same rotational matrix. As long as that is true, these three components combined together is called a vector. Okay, and we can also define the inverse transformation. The inverse transformation is inverse of the R matrix. Okay. The bottom line, in physics, the definition of vector is very specific. We require the three components of this object. They need to rotate exactly the same as x, y, z, the three components of my location, my coordinate. If object rotate in the same way as my coordinate, I call it a vector. So that's a three-dimensional definition. Sorry, that's a definition of a 3D vector. So 3D vector, the most important property is its response to rotation. You need to rotate the same way as coordinates. Okay, so now let's do a little bit of math. Okay, so we know that the 3D rotation can be written in this matrix structure. Okay, for any vectors, it should rotate this way. Okay. And this R, this rotational matrix, is a 3 by 3 matrix, as we showed earlier. Okay, and we can rewrite this matrix formula into its components formula. Okay, so the ith component of the W prime vector and is related with the W vector in this specific way. Okay, so here this R is a Rij is a component, is a 9 components of this rotational matrix, and we need to make sure that the second index is the same as the index of W, and we sum over this J index, and that's the component formula of this matrix multiplication. Okay. And in physics, especially in special relativity and general relativity, we usually follow the so-called Einstein's convention. Einstein's convention says that because we need to do this sum of J. Okay, Einstein's convention basically says let's actually throw away this sum sign. Okay, we don't write down this sum. As long as we have two identical sub-index, two identical subscript or indices, J and J, we do a sum over J. Okay, so that's Einstein's convention. We no longer write down this sum. We still do the sum, but we no longer write it down. As long as we see J and the repeating index J, it means we multiply this together and sum over J. Sum over J equals X, J equals Y, J equals Z. Okay. So from now on, we will not write down this sum anymore. We will use Einstein's convention because of the repeating index. J is a repeating index. J will be summed over automatically. Okay, so that's Einstein's convention, and we will follow this convention. Okay, so the sum sign is gone now. We don't write it down explicitly, but we still need to do the sum. As long as we see the repeating indices, it means we need to sum J equals X, J equals Y, J equals Z. Okay, and the inverse transformation can also be written in the same structure. We just use the R inverse matrix, and Ij is I's and J's component of the R inverse matrix, and we do the same. Okay, so this is a mathematical convention and Einstein's convention to write down this matrix product. Okay, and in addition to vector, we also know that there are some physics quantities that are not vectors. For example, some physics quantities are scalars. Okay, the definition of a scalar very similar to vector. First of all, we have one number. This time is one number instead of 3 components. We have one number, and secondly, and more importantly, we need to require that this number, this quantity, does not change under spatial rotation. Okay. So we rotate our axis, or we rotate our space. This quantity doesn't change. If that's the case, then this is known as a scalar. Okay. And we also know some of the physical quantities are neither scalars or vectors. They are the so-called, say, rank 2 or even rank 3 tensors. Okay. And those tensors, the definition of tensors is the same thing. Okay, so for example, for rank 2 tensor, like what we learned, like the quadruple moment in electrostatics, for example, and for rank 2 tensor, we need to make sure that this object, this physical quantities, has 3 by 3, 9 components. Okay, and more importantly, these 9 components need to satisfy the following relation under spatial rotation. Okay. So under spatial rotation, this tensor W becomes tensor W prime. And the W and W prime is related by the same rotational matrix as vectors. So R is the same rotational vector, it is the same rotational matrices as we used before. But we need to multiply two of them. Okay, one of the R rotational matrices is multiplied for J component, the second component of this tensor. The other one is for the first component of the tensor. Okay? And we can rewrite this into a matrix formula. In a matrix formula, it means this new tensor, this W prime, and old tensor W is related by the rotational matrices R, but we need to multiply one R on the left side, and on the right side, we multiply the transpose of R. Okay? So this formula you can check is exactly equivalent to the component formula we show above. Okay? So the bottom line, in physics, we classify quantities into different groups. We classify them into scalars, vectors, rank 2 tensors, and also rank 3 tensors, etc. Okay? And this classification is not purely based on how many numbers we written together. This classification is actually based on how these physics quantities respond to space rotation. If we rotate the space, how does this quantities change? Okay? If a quantity does not change at all under spatial rotation, we call it a scalar. If the quantity changes exactly the same way as coordinate, we call it a tensor, or we call it a vector, or rank 1 tensor. If a quantity rotates like this, with 2 rotational matrices, then we call it a rank 2 tensor. Okay? And of course, we can generalize this definition to rank 3 tensor. So some quantities in physics, under spatial rotation, it becomes like this. It has 3 subindices. 3 subindices means it has 27 components, 3 times 3 times 3. Okay? And under spatial rotation, we need to multiply 3 rotational matrices to this object. One for the first index, one for the second index, and one for the last index. And if the quantity follows this rotation, response to rotation this way, this is called the rank 3 tensor. And we can keep doing this. We define rank 4 tensor, rank 5 tensor, and rank n tensor, even to infinite order. And in summary, we classify our physics quantities according to their rotations, according to the response to rotations. And depending on how many rotational matrices we need to multiply, we define this as rank 0 tensor, scalar, rank 1 tensor, vector, rank 2 tensor, rank 3 tensor, etc. Okay. It turns out that one can prove for any physics quantity, we can always decompose it according to these tensor structures. We can always decompose it into a scalar, vector, rank 2 tensor, rank 3 tensor, etc. Okay, so this is a way to organize physics quantities. And no matter what physics quantities we are looking at, we can always do a decomposition to split them into different channels. And each channel is either a scalar or vector or matrix, etc. Okay, so this decomposition is actually equivalent to the spherical harmonics expansion we learned in quantum mechanics and EM-M1. Okay. And it is also equivalent to the angular momentum classification in quantum mechanics. We classify angular momentum based on the total angular momentum quantum number L. Well, L is 0, 1, 2, or 3. Okay. There is no half. There's no half angular momentum in this classification. This classification only corresponds to the integer total angular momentum. Okay. Well, nevertheless, we know that we can organize our physics quantities in this way, classify them as scalar, vector, and matrices, and the rank 2 tensor, etc. But why do we do that? Okay, why do we even bother to classify our physics quantity into these groups? Okay, it turns out this classification is extremely useful. It's very useful. And the reason it is useful is because we have a fundamental assumption in physics. In physics, we assume our space is isotropic, which means we assume our physics law, all our physics law, takes exactly the same form, no matter how I choose the direction of my XYZ axis. Okay, I can choose my XYZ axis this way, write down my physics law, and I can choose a different orientation for XYZ axis, and then write down the physics law. These two formulas need to be exactly the same. Physics law should not depend on how I choose my axis. Okay? Physics quantity could. For example, if I rotate the XYZ axis, my coordinate changes, but the physics law never changes. For example, Newton's second law, F equals ma. Okay, force changes. The XYZ component of the force will change if we rotate the axis. The XYZ component of the acceleration will also change if we rotate the axis. But the fact F equals ma never change, no matter how we rotate the axis. And the reason behind that is this fundamental assumption. We assume our space is isotropic. There's no special direction. So any direction I can choose as x, y, z. Okay, so that means all my fundamental physics laws need to maintain the same structure, no matter how we choose x, y, z axis, or no matter how we rotate the system. Okay, and in order to guarantee that our physics laws remains the same structure under spatial rotation, how do we do that? Well, we do that using exactly this classification of physics quantities. Okay, in order to make sure our physics laws take the same form, no matter how we rotate the axis, we only need to do one thing. That one thing is to guarantee, to make sure that our physics law can be written in the structure of scalar equals scalar, or vector equals vector, or tensor equals tensor. Okay, we need to make sure that for any physics law we written down, the two sides of the equation are the same type of object. If the left-hand side is scalar, the right-hand side must also be a scalar. If the left-hand side is a vector, the right-hand side must also be a vector. If the left-hand side is a rank 2 tensor, the other side must also be a rank 2 tensor. We will not allow physics laws look like this. For example, one side is scalar, the other side is a vector, they equal to each other. That cannot work. If we have physics law look like this, our space will not be isotropic anymore. We'll have some special direction. And by rotating the axis, the physics law will behave differently. Okay. So if we recall all the physics law we learned in the previous courses, you probably will notice that all the fundamental physics laws take exactly this form. Okay. So for example, Newton's second law, F equals ma, F is a vector, mass and times a, acceleration is also a vector, etc. Okay. And to realize that this structure is exactly what we need to guarantee that our space is isotropic, or to guarantee the physics law is invariant under rotation, is quite straightforward. Okay, because scalars, any scalar, they satisfy the same. They respond the same way under rotation. So for example, in one coordinate system, we have x equals y. Okay, now let me rotate the axis. Let me choose a different axis, different orientation of x, y, z. Because these are scalars, x doesn't change under rotation. Y doesn't change under rotation. So if I rotate to a different axis, different choice of axis, the physics law is still x equals y. None of them changes. Okay. Similarly for vectors, if I have xi equals yi, the x equals y, so x vector equals y vector, it means all the three components, every component are equal to each other, xi equals yi. Okay. Under rotation, we know that x under rotation behaves like this, with the rotational matrix multiplied to it. Y behaves exactly the same way. Okay, it has exactly the same rotational matrix and multiplied to y. Because I'm multiplying the x and the y by the same matrices, if x equals y, x prime will be equal to y prime. So after rotation, they're still equal to each other, because they rotate exactly the same way. But if I have a scalar equals a vector, that would not work. Okay, if I have a scalar x equals to say one component of the vector y sub I, okay, then under rotation, x doesn't change because x is a scalar, but y changes because y is a vector. Now under rotation, it becomes this. Then in this new coordinate, my formula, my physics law, will be fundamentally different, very different from what we had before. Okay, so if I have scalar equals a vector, because the two sides are different objects, then the physics law cannot stay the same form. It depends on how we choose axis. If we choose a different axis, the physics law will change. And if we believe our universe is isotropic, there's no special direction, then our physics law cannot take this form. Okay. The bottom line, if we want the system to be rotational invariant, if we want our universe to be rotational invariant, we need to make sure our physics law has the same type of object on both sides of the equation, always. Okay, So then before we switch to 4-dimensional space, let me mention one more conclusion, actually review one more conclusion. You may have you may have heard some of this, you may have learned some of this knowledge in undergraduate courses, but let me remind you about the definition of the so-called orthogonal matrices. Okay, so the rotation. Okay, one important property of rotation is that the rotation does not change the length of a vector. So if we have a vector under rotation, the direction, the orientation changes, but the length remains the same. For example, let's say we have a point A and a point B, and there is actually the coordinate, the distance between A and B is, say, a vector described by a vector delta r, and this r is a vector point from point A to point B. Okay, and this vector has 3 components: delta x, delta y, delta z. Okay, and the length of this distance is, of course, delta x squared plus delta y squared plus delta z squared square root. Okay, and this length can also be written in a vector or matrix formula. Okay, so more precisely, let's write down the length square, the square of this distance. The square of distance is delta x squared plus delta y squared plus delta z squared. This can be written as a row vector, delta x, y, z, multiplied by a column vector, delta x, y, z. Okay, so this is actually this is the distance square in a 3D space. And under rotation, we know that the delta x, y, z becomes delta x prime, y prime, and z prime. And this delta x prime, delta y prime, delta z prime is related with delta x, y, z by a rotational matrix, as we know. Okay, and this is for the column vector. And for the row vector, we know that the row vector is a transpose of the column vector. So if the column vector behaves like this, then for the row vector, I just need to take a transpose on both sides. Okay, on the left side, the transpose of this object become another column vector. Sorry, become another row vector. On the right-hand side, to take a transpose, first I need to switch R and this vector. I switch their order, and then I take transpose for R. R becomes transpose of R, and this column vector becomes its transpose. That's a row vector. Okay, so this is the transformation for the row vector. So the column vector and the row vector, they use the same rotational matrix, but column vector use R, row vector use R transpose. Okay, then when I multiply these two quantities together, okay, now I ask, what is the distance after the rotation? The distance after the rotation is delta x prime square plus delta y prime square plus delta z prime square, which can be written in this vector formula. So this is delta x y z prime multiplied by delta x y z prime. Okay, the same distance, but this is a coordinate after rotation. And for delta x, delta y, delta z prime for the column vector, for the row vector, we know the row vector is all the row vector times R transpose, row vector times R transpose. Column vector is delta x, y, z times R, delta x, y, z times R. Okay, so under rotation, after rotation, this distance is this guy, And before rotation, we know the distance is this guy. After rotation, the distance is this guy. And we need to make sure that these two distances always remain the same. So this distance, these two distances are always the same, no matter which 2 points, A and B, we choose. Because rotation does not change the distance. Rotation only changes orientation, does not change the distance. So we need to make sure that this object and this object are always the same, no matter what delta x, delta y, z, delta y, delta z, the value I put in, are always the same. How can we guarantee these two objects are always the same? Well, the sufficient and necessary condition is the matrix in the middle need to be the identity matrix. Okay. Sorry, let me address something. Okay, so this RT times R need to be an identity matrix. So in order to guarantee these two quantities are the same, we need to make sure that RT times R is identity matrix. That's written down here. So this is a condition guarantee that after rotation, the distance do not change. Okay. And I here is a 3D identity matrix. Okay. And in mathematics, matrices satisfy this relation is known as the so-called orthogonal matrices. Okay. Orthogonal matrices means RT times R equals I. It also means that the inverse of R is the transpose of R. Transpose equals to inverse. Okay, so this is actually a real number version of the unitary matrix. So in quantum mechanics, we talk about the unitary matrix. A unitary matrix is U dagger U equals identity. Here is R transpose R equals identity. So these two type of matrices are very much similar to each other, except that the U matrix is a complex matrix in general. But here, rotation matrix is a real matrix. Because it's a real matrix, we don't need to take complex conjugate anymore. So we just need transpose. We don't need Hermitian conjugate. Okay, nevertheless, so this is a mathematical definition of orthogonal matrices. So from this example, we can see here, all rotations must be orthogonal matrices. Okay? All rotational matrices must be orthogonal matrices. But the inverse is not quite true. Orthogonal matrices are not necessarily rotations. For example, this orthogonal matrix is not a rotation. 1, 1, minus 1. Okay, so we can easily check this is an orthogonal matrix. 1, 1, minus 1 times is transpose. This is the diagonal matrix, so transpose is itself. And this matrix times this matrix, you can easily check it's 1. So this is indeed an orthogonal matrix. But it is not a rotation. It's not a spatial rotation. The reason it's not a spatial rotation can be seen here. Okay, if we multiply x, y, z by this matrix, it becomes x times y. It's become x, y, and the minus z. So this is a mirror transformation. Okay, x and y stays the same, but z pointing up becoming pointing down. So this is describe a mirror in the xy plane. Okay, so this is a mirror transformation. It's not a rotation. Okay, so all rotational matrices must be orthogonal matrices, but orthogonal matrices are not always rotations. Okay, it turns out we can classify orthogonal matrices into two groups depending on the determinant. If the determinant is +1, if there is orthogonal matrix R and determinant is +1, then this is a rotation. Okay, but if the determinant is -1, then it's not a rotation. Okay, so determinant -1 the matrices corresponds to rotation followed by a spatial invariant or followed by a mirror. Okay, and the mirror or spatial invariant transformation changes the determinant from +1 to -1. So the bottom line, rotations and orthogonal matrices with determinant +1 has a 1-to-1 correspondence. Okay, every rotation corresponds to orthogonal matrices, orthogonal matrix with determinant +1, and vice versa. Every orthogonal matrix, as long as determinant is +1, it corresponds to a rotation. Okay. And for the determinant -1, you can always separate them into a rotation followed by a mirror, or mirror followed by a rotation. Okay. So orthogonal matrices describe two types of transformations. One is rotation, another is mirror or spatial invariant, or the combination of both. Okay, so that's a mathematical description for rotations. Clear this, and now we can go to the next part. Okay, now let's go back to the four-dimensional space. Okay, so before we discuss about the vectors, scalars, tensors in this four-dimensional space and why we need to define those things, let's prove a quick conclusion. Okay, that conclusion is that Lorentz transformation is very similar to rotation. Okay, and more precisely, we want to show that if we define distance like this, a four-dimensional distance like this, then this distance is the invariant under Lorentz transformation. Okay, so this object is in some sense very similar to a Euclidean space distance. Okay, it's a square of spatial separations of each component plus together. That's the distance square in Euclidean space. Here we are also using squares. Squares in time difference, squares of difference in x, difference in y, difference in z. The only difference is that in 3D Euclidean space, we add them together. It's all plus. But here in the four-dimensional space, the time direction has a plus sign. And all the x, y, z component has a minus sign. Okay? So it's not exactly the same, but very close and very similar to each other. So as you know, this is what we define as four-dimensional distance, or more precisely, four-dimensional distance square of the four-dimensional distance. Okay, so I will not bother you with the detail about how to prove this. I believe most of you have learned how to prove this in your undergraduate courses. Here I just quickly flash to you, quickly show you two ways to prove this. One is a dirty hand waving way, and another one is a more precise and more accurate, more rigorous way. Okay, so one hand waving and easy proof for this to show that this object is invariant under Lorentz boost is to realize this quantity is exactly the proper time we defined in the previous chapter. Okay, so more precisely, this guy is c square tau square, where tau is a proper time. Okay, we know that the proper time is the time that filled by a moving object itself. Okay, and this proper time is the time that measured, say, by a moving clock in its own reference frame. Okay, because it's measured in its own reference frame, the proper time is independent of observer. No matter which observer, no matter which reference frame we are using, once we convert it to the proper time, it's the reference frame of that moving particle or moving racket. And this tau is independent of reference frame. Because the proper time is independent of reference frame, speed of light is independent of reference frame, this combination must be independent of reference frame. No matter what reference frame we are using, we must have the same c square tau square. So that's why this object is invariant under Lorentz boost. Okay, of course, as I mentioned, of course, I said that this proof is a dirty hand waving proof. It's not a rigorous proof. And the reason this is a dirty hand waving proof and not a rigorous proof is that if you think carefully about the proof I utilized, this proper time proof only works when delta t is larger than, when the separation in time is larger than separation in space. Okay. In other words, only if A and B are time-like. Time-like is a concept we defined, we discussed in the previous chapter. Okay. Only if they are time-like, I can use this proof. If A and B, these two events are space-like, space-like means the spatial separation is larger and time separation is smaller. If it's space-like, then the whole quantity is negative. If the whole quantity is negative, then proper time is not well defined. I can't define proper time anymore. So I cannot use proper time to prove it. So this proof only proves the time-like events A and B. This distance is invariant under Lorentz boost. For space-like, I can't use this proof. Okay, and if we want to, but it turns out that for space-like event, this object is also invariant under Lorentz boost. And to rigorously prove that, we just need to utilize the Lorentz transformation. Okay, we know how B coordinate transfers under Lorentz transformation, and we know how A coordinate transfer under Lorentz transformation, and we just plug that in. And I will not go through the detail. And you just plug it in, and through the calculations, you can show that in the old coordinate, in the old coordinate and in the new coordinate, the L, this distance square, always remains the same. Okay, and this proof works both space-like and time-like. So that's a more rigorous proof. Okay, so anyway, in Lorentz transformation, in special relativity, we can prove that this distance, okay, this so-called four-dimensional distance, is invariant under Lorentz boost. Okay, now let's compare Lorentz boost, compare this four-dimensional distance and the four-dimensional Lorentz boost with our knowledge we know about 3D space. Okay, so in 3D space, we know that there are three types of transformation, three types of linear transformation, more precisely, three types of linear transformation that keeps distance invariant. First one is translation. Under translation, distance remains the same. Secondly is rotation. We can rotate our axis, distance remains the same. And the third one is reflection. Okay, so in 3D, if we want to keep distance invariant, and if we want to do a linear transformation to our coordinate, only these three guarantees that distance remains the same. Okay, now we are in four-dimensional space, and we know that Lorentz boost maintains this four-dimensional distance to be invariant. And the natural question to ask here is Lorentz transformation more similar to a translation, or more similar to a rotation, or more similar to a reflection. Okay, because these are the only three possibilities. If Lorentz transformation keeps the distance invariant, it should be similar. It should be a 4D generalization of a 3D transformation of one of them. The question is which one. Okay. First of all, it's easy to realize Lorentz boost is not similar to translation at all. Okay. So one key property of translation is that if you do a translation, every single point in your space need to change. And there is no point that remains at the same position. Okay. Translation changes all the points. Every point is translated. There's no point stays the same. But the Lorentz boost does not have that property. For Lorentz boost, at least the origin stays the same. So in other words, Lorentz boost has a fixed point. This is so-called fixed point. Fixed point means this point before and after this transformation, it stays at the same value. Okay, so the origin does not move. Because the origin does not move, we immediately can realize that this Lorentz boost is not a translation. Translation, every point need to move. So Lorentz boost is not a translation. And Lorentz boost is not a reflection either. Okay, because mirror reflection or space invariant, you need to flip the direction of some arrow. You need to flip the direction of some axis. But if we look at the Lorentz transformation, T prime and T, they have the same sign. You didn't flip the direction. You didn't use a minus sign to flip the direction of T. You didn't flip the direction of X either. X and X prime have the same sign. Y and Y prime have the same sign. Z and Z prime have the same sign. We didn't do any reflection either. Okay? So the bottom line, Lorentz boost does not look like a translation at all because it has a fixed point and translation cannot. And it's not a reflection either because we didn't flip any axis. We didn't flip the direction of any axis. So there's no option. We have to come to the conclusion that the Lorentz boost is more similar to rotations. Okay? It's a 4D generalization of 3D rotations. Okay? And as you have seen in your previous homework, indeed, actually in your current homework this week, indeed, the Lorentz boost and the rotations has a lot of similarities. We showed in our homework, if you look at the small velocity Lorentz boost and the small angle rotations, the operators, or more precisely, the mathematical terminology is the generators. The generator of those operations has very similar commutation relation. And we can combine them together to form the two sets of SU2 algebra. Okay, so rotation, spatial rotation, and the Lorentz boost are very much closely related. And the Lorentz boost can be considered as a 4D generalization of a 3D rotation. Okay. Okay, so the bottom line, Lorentz boost is very similar to rotation. It's a 4D version of rotation. To see this more clearly, let's write down the Lorentz boost in terms of what's that called? In terms of a matrix formula. Okay. So here, let me introduce a convention that we will frequently use in the rest part of the semester. We will introduce a 4-dimensional coordinate x0, 1, 2, 3, 4. So now instead of t, x, y, z, I will often use 0, 1, 2, 3. Okay, 0 means time. Okay, and more precisely, 0 means speed of light times t times time. Okay, and the reason I want to multiply a speed of light here is because speed of light times time gives me the dimension, gives me the unit of spatial distance. Okay, so CT has the same unit of x, y, and z. Okay. Adding this factor makes x0, y, and 2, 3 have the same unit. That's the reason of this speed of light. And for the 1, 2, 3 component, they are just x, y, z. They're my old friend of spatial coordinate. So now I can write this 4 object together, and this 4 object together, and I will argue this is a 4-dimensional. This is my 4-dimensional coordinate, and it's a 4-dimensional vector. Okay. Okay, so it has 4 numbers together, and I argue this vector. But we know that in order to claim this is a 4-dimensional vector, 0, x, 0, 1, 2, 3, we need to have rotations. Right? So as we showed early on in 3D space, the reason we can classify things into vectors, tensors, scalars, blah, blah, is not because we have 3 numbers written together. It's because these 3 numbers written together, it has a rotational, it has a response to rotation. We need to define rotation. Okay. And that rotation turns out to be Lorentz boost, and also the spatial rotation. The spatial rotation rotates the spatial part, the last three components. The Lorentz boost rotate between the first component and the rest three. Okay. So in this coordinate, in this 4-dimensional coordinate, I can rewrite my Lorentz transformation in this way. Okay. The formula is almost exactly the same as before, except that my x0 now here has a speed of light built in. Okay, the formula modified a little bit, and we can write down this Lorentz transformation, Lorentz boost in a matrix formula. Once we written down this matrix formula, we realize that it's actually very similar to 3D spatial rotations. Okay, so the matrix formula here, it's we can rewrite this matrix formula. Let me call gamma to be the cos h of some quantity. Okay, and if this one is cos h, this off-diagonal component is the sinh, sin h. Okay, and the reason this is cos h is sinh is because we can easily prove the square of the diagonal component minus the square of the off-diagonal component is 1. So if this is cos, we can call this quotient and this sinh. Okay, so this is not so important. We just define this object as cos h and this one as sinh. Okay, and we can compare this object with 3D rotations, and we realize that the transformation of Lorentz boost and the 3D rotations are very similar to each other. It's a 4-dimensional version of 3-dimensional rotation. Here, there are only two differences. Okay, one difference is that for 3D rotation, we use sine and cosine. Okay, the square of the diagonal component plus the square of the off-diagonal component is 1. But for Lorentz boost, we use sinh and cos h. And the diagonal component square minus off-diagonal component square is plus 1. Okay, that difference comes from the fact that in our 4-dimensional distance, we have sometimes plus sign, sometimes minus sign. Where in 3D, the distance is defined with plus sign only. Okay. And another difference is that in this Lorentz boost, the two off-diagonal components have the same sign. Where in the 3D rotation, they have opposite sign. This difference also comes from the fact in 4D, the distance is defined with both plus and minus sign, but in 3D, it's just a plus sign for the distance. Okay, but nevertheless, this difference is minor. Okay, and the similarity is strong. So Lorentz boost is very similar to a 3-dimensional rotation. Okay. So here I highlighted the fact that all this distance comes from fact we have both plus and minus terms in the definition of 4D space, 4D distance, but in 3D it's always plus. Okay, so a couple of points to highlight. First of all, in Newton's mechanics, in Newton's framework, we don't have Lorentz boost. In Newton's mechanics, we have the so-called Galilean transformation. Galilean transformation is not a 4D rotation. Okay? To realize that, the simplest way to realize that is to look at the time dimension. Time dimension in Galilean transformation is always independent of space. Okay? Time always remains the same, no matter how do you transfer the reference frame. So in Galilean transformation, it is not a rotation, because if you have a rotation, you need to be able to rotate one axis to another, say space to time. But in Galilean transformation, space can never be rotated to time, so that's not a rotation. And that is the reason why in Newton's mechanics we never talk about 4D vectors or 4D space. We don't. We think about the universe as 3-dimensional space plus one additional dimension time. But this time dimension and this spatial dimension, spatial cannot be rotated into time. They are separate objects. So 3D space and one additional dimension of time, and they don't rotate to each other. The reason in special relativity, we call it a 4D space, we merge space and time, is because of Lorentz boost. Lorentz boost really introduces us a rotation and allow us to rotate between space and time. once we can rotate between space and time, we cannot separate them anymore. We have to write space and time together as one object, and that object is our four-dimensional coordinates. Okay, and that's the reason why this the concept of this four-dimensional space-time only becomes important in special relativity. Okay, so this story is actually very similar to the story we mentioned earlier, right? So in earlier on, we said that the age, height, and the weight of a person, you have three numbers, but we will not call it a vector. Okay, and the reason we don't call it a vector is because we cannot define rotation to rotate in this three dimensions, to rotate these three quantities. Okay, without a rotation, it cannot be called a vector. You write three numbers down, it's three numbers, but we can't rotate them into one another. And but once we can rotate, once we have an object to rotate these three numbers to each other, suppose one day we discovered some physics law that allow us to do a transformation between these three quantities, then it will become a vector. And then we will call it a three-dimensional space. Okay. So for space-time, in Galilean transformation, in the Newton's framework, time is separated from space. So it makes no sense to combine them together to call it 4D. But special relativity really allows us to define a rotation. And that rotation rotates space into time and time into space. And that's why we have to group them together now as a 4D object. Okay, so that's the reason why we need to go 4D. And finally, let's do some quick review again about mathematics. Okay, so so this is something we just discussed earlier today. Okay, so we know that in 3D space we can define distance square, and we can write down distance square in this structure: row vector times column vector. And the row vector and column vector, they rotate according to the rotational matrix, and the rotational matrix make sure that distance is invariant because it's orthogonal matrix. Okay, so in order to help us generalize this same type of physics, this same type of relation into 4D space, let me rewrite this definition of distance in a slightly different way. Okay, so we know it's a column vector times, a row vector times a column vector. Now between this row vector and column vector, let me insert identity matrix. We know that identity matrix don't do anything. Identity matrix times anything is just itself, right? So this doesn't change the definition. It's the same definition. I added the useless identity matrix in between. Okay, and I will call this identity matrix G. This G is a so-called metric tensor, and the metric tensor tells us how do we define distance. And the 1, 1, 1 plus 1 plus 1 plus 1 here means our distance L squared is defined as plus 1 delta x plus 1 delta y squared plus 1 delta z squared. Okay. So this 1, 1, 1 plus 1 plus 1 plus 1 here means this number is plus 1, this number here is plus 1, this number here is plus 1, and this is the so-called metric tensor. Okay. So it's exactly the same thing, just I inserted this metric tensor in the middle. And this metric tensor don't do anything in 3D Euclidean space. Okay, let me erase this. Okay, so now let's look at this rotations in the presence of this metric tensor. Okay, if we put the metric tensor here in the middle, it doesn't do anything. Okay, we can still do the rotation. Okay. After rotation, x, y, z becomes x prime, y prime, z prime. X, y, z become x prime, y prime, z prime. And this x prime, y prime, z prime, and my original x, y, z is related by a rotational matrix. The column vector is also column vector multiplied by rotational matrix. The row vector is multiplied by the transpose of a rotational matrix. Column vector is multiplied by rotational matrix. Okay, so it's RT, G, R. Okay. It's the same formula as we have before. The only difference is I keep my G, my metric tensor in the middle. Okay. Now again, because I want the distance to remain the same under spatial rotation, which means this matrix G and this RTGR need to equal to each other. Okay. In order to make sure my rotation does not change my distance, I need to make sure R transpose times G times R equals to my metric tensor. In other words, I need to make sure that all my rotational matrices does not change my metric tensor. Okay. So this RTGR is how the metric tensor is rotated. It's a response to spatial rotation. Okay. So metric tensor is a tensor. As we know, for a tensor, it responds to rotations with two rotational matrices, one on the left side, one on the right side. Okay. So this is very similar to what we learned in quantum mechanics. In quantum mechanics, we know that if we do a changing of basis, the quantum operator behaves like this. Okay. And this condition in quantum mechanics means we want the quantum operator to be invariant under the basis, under changing of basis. Here, it means we want the metric tensor to be invariant under the rotating of coordinates. Okay, so nevertheless, this is constraint. Okay. As long as my rotational matrix does not change my metric tensor, distance is invariant. Okay. Of course, in 3D space, this metric tensor is just identity, so this condition gets simplified into RT times R equals identity. That's a condition of orthogonal matrix as we defined before. Okay, but if the metric tensor is not identity matrix, the lower formula is still right. So this lower one is a generic formula. No matter what metric tensor we have, if we want the rotation to not to change the distance, we have to satisfy this. And the formula on the top, RT times R equals identity, the orthogonal matrix condition, only works for the special case where G is identity matrix. Okay, so the lower one is more generic. And this one is what we are going to follow in order to generalize the rotation to 4-dimensional space. Okay, so that's a quick review about 3D. Now let's look at 4-dimensional. Okay, in 4D, we know that our distance is defined this way. Okay, and remember I introduced the new terminology or new convention. X0 is c times t, x1, 2, 3 are x, y, z. In this new convention, this distance square is actually delta x0 square minus delta 1 square, delta 2 square, delta 3 square. Okay, it's just a changing of convention. Okay. And this convention is nice because this convention we can immediately written down this distance square into the matrix form. Delta x 1, 2, 3, sorry, 0, 1, 2, 3, delta x 0, 1, 2, 3, with a matrix in the middle. And this matrix is my metric tensor G. Okay, and this metric tensor G is not an identity matrix anymore. It's because we have plus sign for the first one and the minus sign for the 1, 2, 3 component. Okay, so this plus sign gives me this plus 1, but for the rest 3, I need to have minus 1. Okay, so this G is not identity matrix. This is the reason why we cannot use the orthogonal matrix condition anymore. We need to keep this G in special relativity in the 4D space. In 4D space, we need to explicitly write down this G. Okay, and the rest part of the story is very similar to 3D. Okay, we have a 4-dimensional rotation. Say we have 4-dimensional rotation, and we want to make sure that this 4-dimensional rotation preserves this distance. L squared does not change. Okay, and if we want this 4-dimensional distance to, 4-dimensional rotation to preserve this distance, then the condition is this guy, as we highlighted on the previous slides, on the previous page. Okay, we need to make sure that this 4-dimensional rotation, the matrix of this 4-dimensional rotation, satisfies this relation. R transpose times metric tensor times R equals to G. Okay, so as long as this condition is satisfied, the distance between two events, for the 4D space-time, will remain the same. Okay. Now the question is, how many different types of matrices or how many different types of transformations can satisfy this condition? Well, it turns out there are four types and only 4 types of transformation that satisfy this relation. Or actually, more precisely, 4 types of transformation and their combination. Okay, we know that if operation A does not change distance, operation B does not change the distance either, then I can first do an A transformation, then do a B transformation. The distance will maintain, right? So we have 4 types of transformation maintain this distance. Then their combination, when we combine those transformations together, we'll still maintain the distance. We'll still keep the distance invariant. Okay. But nevertheless, we can classify these transformations into 4 categories, okay, and only 4 categories. Let me look at one of them at a time. Okay, the first one is the obvious one. This is the so-called time invariant. Okay, if we flip the direction of time axis, flip the arrow of time, change the first component. The first component, by the way, is time, to minus itself. Then this transformation is described by this matrix. So the time axis flip sign, XYZ axis stay the same. This operation is typically called capital T. Capital T means time reversal, okay? Time invariant or time reversal. And this time reversal operation, one can easily verify for the metric tensor we defined up there. It does not change the metric tensor. Metric tensor stays the same. Okay? If we flip the direction of time, distance, 4D distance, stay. The second one is the spatial invariant or space invariant, also called parity in particle physics. This one, the time axis stays the same, but the XYZ component changes sign. Okay. If we define the transformation matrix, this transformation matrix, the time dimension is +1, but the 3 spatial dimension are -1s. So 1 + 1, 3 - 1. Okay. And this transformation is usually called P. P stands for parity. Okay. And the P looks like this, and it's easy to check P times G, P transpose times G times P. Still is G. The metric tensor stays invariant. So it means that when we flip the direction of XYZ to -XYZ, space invariant, metric tensor remains the same. A metric tensor remains the same means the distance remains the same. This transformation does not change distance. Okay. The third one is spatial rotation. Okay. Spatial rotation, this is our old friend of the 3D space rotation. So the time axis does not change. Time axis is 1, doesn't change. But the 3 spatial dimension changes according to a spatial rotational matrix. And this 3x3 block is just one of the 3D spatial rotation matrices we discussed earlier. Okay. It's also easy to check that this object, the metric tensor, does not change under R transpose times R. Okay. Okay, so this is a 4-dimensional matrix for 3-dimensional rotation. And this is quite obvious because 3D rotation does not change the spatial part. Okay, and 3D rotation does not change time either. So the 4-dimensional distance still survives. So that's the third category that makes this 4-dimensional distance preserved. The last one is Lorentz transformation, Lorentz boost. And for Lorentz boost, the transformation matrix is like this, as we showed earlier. Okay, and one can easily check if we multiply. Oh, sorry, this should not be called R. This should be called L for Lorentz boost. Sorry, I used the same notation. Anyway, so if we call this matrix R, then it's easy to check that R transpose GR equals G. G doesn't change under this Lorentz boost. So here is a detailed proof of this relation. The calculation looks long, but it's not very complicated. It's basically just the multiplication of matrices. And by doing the multiplication of matrices, we can show that indeed Lorentz boost, under Lorentz boost, the metric tensor remains the same. Okay, so that's the 4 types of transformation that preserve metric tensor, and that preserves distance. Okay, and we can further prove that for any transformation, as long as it preserves the metric tensor or preserves the distance, then we can show that it's either one of these 4 or some combination of these 4. Okay? It's either one of these 4 or you can do the combination. Combination means you first do, say, a rotation, spatial rotation, then do a Lorentz boost, then you do a space invariant, then you do a time invariant. Okay, any order you like, any combination would preserve the distance. So these 4 transformations and their combination. If you have a transformation that preserves distance and preserve metric tensor like this, it must be one of these 4 or their combination. And secondly, you can also prove that among these transformations, we can classify them into 2 groups, depending on the determinant of R, determinant of this matrix. The determinant of this matrix, very similar to 3D rotation, the determinant of this matrix can be classified into 2 groups, either +1 or -1. The +1 If it's +1, then it must be either a space rotation or a Lorentz boost, or the combination of the two. Okay, so this space rotation and the Lorentz boost and their combination is known as the four-dimensional rotation, and more precisely, this is known as SO13, and some books call it SO31. Okay, so in 3D rotation, the rotational group is the Lie group is called SO3. 3 here means 3D space rotation. Okay, and in special relativity, in the 4D space, the rotation is called SO13. 1 here means there's 1 dimension of time. 3 here means there are 3 dimensions of space, x, y, z. And the reason 1 and 3 is separated is because in the definition of the metric tensor, one of them has plus sign, the other 3 has minus sign. Okay. So SO3 means the rotation that keeps the metric tensor +1, -1, -1, -1 invariant. Okay. So Lorentz boost and the space rotation combined together gives us this SO3 group. This is the 4-dimensional version of a 4-dimensional generation of a 3-dimensional rotation. Okay. Okay, so for those who are interested in Lie groups or who are familiar with Lie groups, I want to briefly mention that the relation and the difference between the SO13 and the so-called SO4. The so-called SO4 group is a rotation of a 4D Euclidean space. Okay, if you have a 4D Euclidean space, the rotation are known as SO4. The rotation forms a group known as SO4. SO4 are the rotations that keeps the metric tensor +1, +1, +1, +1 invariant. So if you have a metric tensor +1, +1, +1, +1 along the diagonal identity matrix, 4x4 identity matrix, then rotations that keep that metric tensor invariant is called SO4. Okay, that's a so-called 4D Euclidean rotation. Special relativity is a little bit from 4D Euclidean space. This is so-called 4D Minkowski space. And in 4D Minkowski space, everything remains the same, except that we flip the sign of the first component in my metric tensor. I flip the sign of this guy. Oh, sorry, I flip the sign of the other 3. I keep this one to be +1. I flip the sign of the 3 spatial component. So my metric tensor is +1, -1, -1, -1. Okay. So if my metric tensor is this, and I want to make sure that this metric tensor stays invariant under rotation, then I need to use the so-called SO13. And SO13 is basically Lorentz boost, 3D spatial rotation, and their combination. Okay, so that's the second part. Okay, and this transformation is related with 4x4 matrices that satisfy these 2 conditions. The first condition is it makes the metric tensor invariant. The second condition is determinant equals +1. Determinant equals +1 tells us this is not an invariant, not a time invariant or spatial invariant. Okay, so that's the mathematical terminology about this 4-dimensional rotation. Okay, so the bottom line, Lorentz boost and the 3D spatial rotation combined together really give us a 4D rotation. It's a little bit different from 4D Euclidean space rotation because the metric tensor is a little bit different. It's +1 and -1 combined together. But the algebra and the mathematics shares a lot of similarity. So SO4 and SO13, these 2 Lie groups are slightly different, but they share a lot of common properties. Okay, so in the physics picture, we can think about this just as a 4D rotation. Just this 4D space is a little bit different from Euclidean space. The metric tensor is a little bit different. Nevertheless, now since we have this 4D rotation, or SO13, we can now define our scalars and vectors. Okay, and how do we define our scalars and vectors? Well, so first, we define our 4D rotations. The 4D rotations are Lorentz boost and the spatial rotation, or their combination. Okay, then we say any object, if under Lorentz boost and the spatial rotation, they behave the same as our coordinate, that is our 4D vector. If under Lorentz boost and the spatial rotation, this quantity never change, then that is a scalar. So we have scalar, vectors, and we can use this to define tensors, etc., in the same way as we did in 3D space. Okay, the bottom line, if we have a physical quantity that we can organize 4 numbers together, and these 4 numbers under Lorentz boost and spatial rotation rotate the same way as the coordinates. Then we say this is a vector. So that's the definition of 4D vector. Okay, and let's look at some examples. So one of the important examples of 4D vector is space-time derivatives. So space-time derivative is a very important object, especially in E and M, because in E and M, all physics laws is written in terms of partial differential equations. The same is true for quantum mechanics. Everything like our Schrodinger equations is written in terms of partial differential equations. And for all these physics laws, we need partial derivatives. So we have to figure out what are these partial derivatives. How do we organize them into this scalar, vector, and tensor structure? And first, let's define space-time derivatives. Okay? So because I'm using this new coordinate x0, 1, 2, 3, for the 0 direction, I need a little bit of work. The 0 direction is not quite time, it's speed of light times time. One can prove that this zero direction derivative of x0 is actually derivative time multiplied by 1 over c, with the c in the denominator. Okay? So the reason is quite straightforward, because x0 is c times t and c is a constant. So I got this additional c constant. And if you want a more rigorous proof, this is a more rigorous proof utilizing the chain rule of partial differential equations, of partial derivatives. Okay, and if you're interested in the details, you can look at it. And we know that the under Lorentz boost, the coordinate x0, 1, 2, 3 transfers like this. That's Lorentz boost. And we can also define the inverse Lorentz transformation that transfers me from the x prime back to x. And transformation and the inverse transformation are almost the same, except of the opposite sign for the velocity. Okay? This is reasonable because if we have 2 reference frames, k and k prime, the relative velocity between k and k prime flip sign, depending on whether we're talking about k to k prime or k prime to k. We have opposite relative velocity, depending on which way we want to go. Okay? And that opposite velocity is this opposite sign here in the transformation and the inverse transformation of Lorentz boost. Okay? And if we know the transformation for coordinates, we can immediately write down the transformation for derivatives, utilizing the so-called the chain rule of partial differential equation. Okay? So we want to calculate derivative of x prime, and we know x prime depends on x0, x1, x2, and x3. Then we can take the derivative for x and then multiply it by this coefficient, this partial derivative. So this is just the chain rule of partial differential equations. And in this chain rule, we need these derivatives. Okay, we need partial x0 and partial, say, for example, partial x0 prime. And these derivatives can be calculated here. Okay, we know x0 is x0 prime times gamma. So this derivative just gives me gamma, and so on. Okay, so by going through the chain rule, we can write down immediately that the partial differential, operator, partial derivative operator, follows this transformation. Okay? So this transformation can be written down in the matrix form, similar as what we had before. And I want to highlight to you this matrix here we find for the transformation of partial derivatives is actually not the Lorentz boost matrix, but the matrix of the inverse Lorentz boost, inverse transformation. Okay. Remember, for Lorentz transformation, as we showed here, it has a minus sign. For the inverse transformation, it has a plus sign. And for derivative, it follows plus sign, the same as the inverse transformation for coordinate. So for the derivative, we're going from no prime to prime. And that matrix is the same as the coordinate goes from prime to no prime, opposite way. Okay, and which means this derivative is not quite a vector. Okay, but it's not so far away from vector. We need to do some small modifications. Okay, the small modification is the following. Okay? We add 3 minus sign here and 3 minus sign here. Okay, so my partial derivatives, the 4D vector, is not this guy. It's not just write down the 4 derivatives together. Instead, we should use this one. The partial derivative for the time axis, the second component is negative partial derivative for x. The next one is negative partial derivative for y. Negative partial derivative for z. Okay? if we use this one as a definition, if we use this combination, this one is actually a 4D vector. Okay, one can easily check by adding this minus sign here, the transformation matrix here, take this minus sign, same as the Lorentz transformation. Okay. In other words, for partial derivatives, if we want to define a 4D vector, the 4D vector of partial derivative is this guy, not just naively partial 0, partial 1, partial 2, partial 3. Okay. So it's probably a good time to introduce some additional terminology here. Okay. So in special relativity, especially in general relativity, we distinguish two types of vectors. One is a so-called contravariant vector. The other is a so-called covariant vector. Okay. Contravariant vector is what we currently call the vector. Okay. So right now, all the vectors we are talking about here are the so-called contravariant vector. Contravariant vector means these four objects, these four components rotate the same way as my coordinate. If it rotates the same way as the coordinate, I call it a contravariant vector. So my coordinate x0, 1, 2, 3 is a contravariant vector. And for derivatives, partial 0 minus partial 1 minus partial 2 minus partial 3 is the contravariant vector. But at the same time, we can also define the so-called covariant vector. Covariant vector is exactly the opposite as contravariant vector. Under transformation, under say Lorentz boost and spatial rotation, it transforms as an inverse transformation. Okay. For example, derivative, this guy, partial 0, partial 1, partial 2, partial 3. This one under Lorentz boost, it transforms as the inverse matrix. Okay. So this type of object is called the covariant vector. It is almost a vector. It's almost the same as the vector we are using. It's almost the same as the contravariant vector we are using, except that their matrix is exactly the inverse of the coordinates. Okay, so this is a so-called covariant vector. So the naive derivative, if you naively written down 4 derivatives, it's a so-called covariant vector. It's the inverse. The transmission is the inverse of contravariant vector. Okay, so in our course, we were not carefully distinguish these two. Okay, but if you want to learn special relativity, it's important knowledge, it's important convention to distinguish them. In special relativity, we have to distinguish these two. Okay, sorry, this is exactly opposite to what I want to say. Sorry for that. So in our course, because we are studying special relativity, in special relativity, we don't have to carefully distinguish them. We can live with, just without introducing these two concepts. Okay, and in most part of our lecture, we will not carefully distinguish contravariant and covariant. We are not introducing this terminology. Our vector, we will just say we have vector. And when we say we have vector, we actually means contravariant vector. Okay? We don't use covariant vector in most part of our lecture. And occasionally, I will show you the formula that distinguish contravariant and covariant vector. Okay, and if you want to learn general relativity, you have to get familiar with this terminology of contravariant and covariant vector. In general relativity, we have to distinguish them. Okay, the reason is in general relativity, the metric tensor is more complicated. If the metric tensor is more complicated, this convention, this terminology of covariant, contravariant vectors helps a lot. For special relativity, it's not that important. For special relativity, the metric tensor and the inverse metric tensor are the same matrix. So it doesn't make too much difference. Using this terminology is fine, makes formula actually convenient in some way, but we can live with, without using this terminology. So in our lecture, we were not using this terminology, but occasionally I will show you if we use this terminology, what the formula will look like. Okay. Before we skip this part, before we stop talking about covariance vector, let me introduce you one important convention people often use in general relativity. Okay, in general relativity, where we have to distinguish these two, contravariant and covariant, now there, contravariant vectors, we use upper indices for contravariant vectors. So in general relativity, if you see index above the object, it means this is a contravariant vector. If you see index beneath, then it is a covariant vector. Okay, so in general relativity, we use the upper indices and the lower indices to distinguish whether a vector is contravariant or covariant. In our course, again, we were not introduce this terminology, or most part, we will not introduce this terminology. So we will always use the lower indices. Okay, but when we use the lower indices, please keep in mind if you want to compare some of our formula with the other formula who utilize this contravariant and covariant convention, sometimes we need to convert them. So that's a good thing to keep in mind. Okay, so if you see upper indices and the lower indices in some literature, in some reference, you will understand that they are actually referring to the covariant and the contravariant vector. So in Jackson's book, actually there is one section in Jackson's book discussing about this. If you want to learn more the details, you can look at Jackson's book section 11.6. Okay, so the bottom line, nevertheless, partial derivative, if we introduce 3 minus sign, this will be a vector, same as our coordinate. This is the so-called contravariant vector derivative. And naively, if we write down the derivative without the minus sign, this is the so-called covariant derivative. And this is a contravariant derivative. Contravariant derivative behaves like vectors, as we say. And the covariant, it's also like a vector, but the transformation has a minus sign in the velocity. It's an inward transformation. Okay, I think this is a good point to stop. So let's summarize today's lecture. So in today's lecture, we first reviewed about rotations in 3D space. Then we showed that this concept of 3D rotation can actually be generalized to 4-dimensional space and time, because the Lorentz boost serves as a rotation. Okay? By combining 3D rotation with Lorentz boost together, we defined a rotation in 4D space and time. And this 4D space and time enables us to define vectors in 4-dimensional space. And the Lorentz boost and the 3D rotation rotate these 4D vectors in this 4-dimensional space. Okay, and as we will show in the next chapter, this 4D rotation is actually very important in physics and in special relativity, because we want our physics laws to stay the same in different reference frame. If we want our physics law to stay the same in different reference frame, it means we want our physics laws to stay the same structure, no matter how we do Lorentz boost, or no matter how we do this 4D rotation. Okay, so it'll be very similar to 3D. In 3D, if we want our physics laws to stay the same under different rotations, we want to organize quantities into terms of scalars, vectors, and tensors, and make sure our physics law is scalar equals scalar, vector equals vector, tensor equals tensor. In 4D, because Lorentz boosts behave just like a rotation, the story is exactly the same. If we want our physics law to stay the same under spatial rotation and the Lorentz boost, in other words, we want the physics law to stay the same under 4-dimensional rotation, then what we need to do is very simple. We need to organize our physics quantities in terms of 4D vectors, 4D scalars, 4D tensors, and make sure every single physics law we written down satisfies this relation: scalar equals scalar, vector equals vector, tensor equals tensor. That will automatically guarantees us that all our physics laws stay the same in different reference frame. And that is actually a very strong constraint. And we will show in the next chapter that constraint tells us a lot about dynamics in special relativity. With that constraint, we almost have no other option. And there is almost only one possible dynamic we can write down. That's the dynamics of special relativity. And next chapter, we will utilize this constraint to show you, as long as we assume speed of light is for the observers, and as long as we assume all different reference frame sees exactly the same physics law, then we have to come to the conclusion where energy is mass times speed of light squared. Okay, so I think this is a good point to stop. We will continue our discussion about 4D space and then dynamics of special relativity in the next lecture. And see you next time.